Well, hi everybody. We're going to have a fascinating little look today at an area which was really from last year's study, but we really need to give it a bit of a top-up so that we'll be prepared in case they spring anything on us in this vein in the end-of-year exam. So what it is review of counting methods, da-da-da-da, and a lovely blue border. Now, this has given students in Year 11 some fairly substantial headaches, probably increased the headache tablet sales substantially around about the time when they did this, but never fear, your headaches are ended because we're going to give it a nice little top up and it'll be easier for you this time. It always is the second time around. So what are we going to do? We're going to find the number of 6-digit numbers which can be formed from the digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 if each digit A can be used only once and B can be used more than once. Well, how fascinating is this? So I think we better have a go at A first. Now, if they can be used only once, we call that sampling without replacement. Okay? The very first question, though, to ask yourself is, does the order of the digits matter? Does it make a difference if we swap the order around? Does that make them into different little beasties? Well, yes, it does for numbers. So yes, if the answer is yes, we have permutations, which are called arrangements as well. If the answer is no, then we have combinations, which are called selections. I use the terms permutations and combinations. In this case, yes, it's a big yes, so we're going to use permutations. And I like to use the window box technique. Now, there's a little bit of a kicker in this question, guys. It's not just a straight permutations question because there's a bit of an uncertainty over the first digit. You see, the first digit can't be a 0, okay? Can't be a 0. Otherwise, that digit then doesn't count as part of the number. A leading 0 doesn't count, does it? So really, how many choices have we got for the first position? Well, I think we've only got 9. And you thought we had 10, didn't you? Well, that's all right. Never mind. It's easy to get these things a bit confused, and that is it's a difficult little twist to that one, that little leading 0 trick. So anyway, we've now chosen one of our 9 available digits for the first position. How many digits do we now have left for the second position? Yeah, we have 9 because we can have a 0 from here on in, okay? And for the third position, for each of those 9 in the first position, which give rise to a choice of 9 for the second position, we have now a choice of 8 for the third position, and for each of those permutations, we now have 7 available for the next, 6 available for the next, and 5 available for the next position. So therefore, because it's like a gigantic, enormous, sprawling tree diagram arrangement, in fact it's probably a tree forest, really, but you could never practically write that all on a piece of paper. It'd be too massive. So it really is 9 times 9, but because for each of those first 9 there's 9 available for the second position, and then for those 9 of which give rise to 9 each, we have 8 available for the next position, and so on. So it's a multiplication thing, and it comes to 136,080 ways. Thank you, Mr. Box. How do you like it? Not bad, eh? So yes, as I said earlier, you call that without replacement because once you've used a digit, it's not available anymore for the next position. Okay? Good show. Yes, we did see the light. Thank you so much. It was a bit tricky there at the start, but we saw it. Okay? Thank you, Mr. Light. Now, over the page we go, and we're going to do B now. B for you and me, and we're allowed to use the digits more than once. Okay? So that's sampling with replacement. You put it back each time so you can choose from it again after each successive position has been sorted out. Okay, now here's our window box. Now come on, now how many choices do we have for the first position? How many choices? Can we use a 0? Don't think so. So therefore I say there's 9, not 10. Now we're allowed to use a 0 from here on in because that as long as the leading digit's not a 0, as long as it's a a non-zero digit in the first position, then we can have as many digits zeros as we like from then on in. So I say every position there gets a 10. Don't you? Think so. Unless I'm massively wrong, in which case I'm very happy to admit it, but I don't think so. So that gets, let's see, 900,000, doesn't it? 900,000 ways. Good gracious me, that's a lot. Thank you, Mr. Box. So I think that's it, isn't it? Yes, that's with replacement. That's so you see the distinction? Yeah, it is different. Righto, now what are we doing now? We've got to find the number of ways of arranging 3 books on a bookshelf from a choice of 10 books, alright? Now what's the first question you always ask, guys? Does the order of the books matter? Does it make a difference? Does it change it into another permutation, or do you know what I mean? Another different a different configuration is what I'm trying to say. Well, yes, it does, because the order does matter if you're doing books, arranging books. Of course it does. Now, so therefore, we've got a permutation situation, so we're going to use permutations. Now, I think I like the idea of using the window box again, and we've only got 3 books, but we're choosing from 10. So we've got 10 choices for the first position, and for each of those 10 we have a choice of 9 for the second position, and for each of those 10 in the first position, which give rise to 9 each for the second position, we have 8 available each for the third position. So there is our total number of permutations, which gets us 720. Okay, that's without replacement, of course. It is. So, or we could have done it this other way. This is a straight permutations question with no tricks like that number thing above. So we could just say, well, it's 10p3, choosing 3 from 10, which gets us 10 factorial over 10 minus 3 factorial, which is 10 factorial over 7 factorial, and we're going to have a massive cancelling here. 7's cancel, 6's cancel, 5's cancel, 4's cancel, 3's cancel, 2's cancel, and we just get what we got above. 10 times 9 times 8, which is 720, and Mr. Box is awaiting. Thank you, Mr. Box. Get it? It's rather marvellous, isn't it? It's good to exercise the brain. Right. Now we've got 4 boys and 3 girls sitting in the front row of a classroom. How many different ways can they be arranged? A, if there's no restriction, and B, if there must be a boy at either end, meaning at both of those ends. Alright, let's go for A. That's a nice one, no restriction. So now, you have to ask yourself, guys, does the order of the boys and the girls matter? Does it make a difference if we switch them around? Yes, it does. It does, because you get a different configuration then. So yes, it does. So we're dealing with permutations. That's always the first question you ask with this stuff. Right, let's do, I think we'll do the window box, don't you? I like that window box technique. So for the first position we've got 7 available. That's how many we've got. And we're going to use up all 7 positions. So yes, you guessed it, it's 7 times 6 times 5 times 4 times 3 times 2 times 1, which gets us, courtesy of Mr. Calculator, 5,040 ways. Thank you, Mr. Box. Good? You like that? Okay, and that's without replacement, of course, because you get less choices for each successive position, yeah? Here comes the straight permutations way. Basically, we're choosing 7 from 7, aren't we? Okay, so that gets you 7 factorial over 7 minus 7 factorial. Now, 0 factorial is 1, guys. So you better tuck that one away in your memory banks. Don't get confused by 0 factorial, it's 1, alright? So that just simply gets us 7 factorial, which is what we got in the window box above. Yeah, 5,040 ways, thank you, Mr. Box. Feeling good? Definitely. Here comes B. Okay, now this is very tricky. We've got to have a boy at either, or meaning both of those ends. Now, I think window boxes, when you get tricky ones with these permutations, look, just do a window box, you know. That's the way to go. So the way I figured this one out was, I thought, well, let's do the ends first. Now, at the left-hand end, how many boys have I got to choose from? Because we're only doing boys because they have to be boys at the ends. Well, for the left-hand end, I say we've got 4. And what about the right-hand end? Well, we've already used up one boy, so to speak, and therefore we've got 3 available for the right-hand end. Now, what goes in the other boxes? What do you think? Well, how many people have we chosen from the list from the available 7 people now? We've actually chosen 2, haven't we? So how many choices do we have now to put in that second box from the left? We've got 5. That's right. And therefore, for the next box, we've got 4. For the next box, 3. For the next box, 2. For the next box, 1. And that is it. And that comes to 1,440 ways. And thank you, Mr. Box. Wasn't that nifty, eh? Very nifty. Feeling good? No problem. Let's forge ahead. We've got a committee to be chosen from 5 men and 8 women. Okay, find the number of possible committees of 5 people which could be formed. A, if there's no restriction. B, if the committee must contain 2 men and 3 women. And C, if the committee must contain at least 3 women. Alright, come on, we'll do A. Yeah? And what have we got? No restrictions. Okay. So, we've got 5 positions, haven't we? 5 positions. Okay. Well, the first question to ask yourself is, does the order of the people in the committee make a difference? Well, I certainly hope not. I don't think it does, do you? No, if you had Joe and Margaret, is that the same as Margaret and Joe? Well, of course it is, if they're both in the committee. So the order doesn't matter. So this is combinations now, not permutations. Okay, so that's a really key bit of insight to get so that you don't go wrong. Right, now, we have no restrictions. So basically we're picking 5 people from a total of 13. Yeah, there's selections. Yeah, I get that. Thank you, Mr. Computer. We're choosing 5 people from 13, and that gets you 13C5, yeah? Now, the formula for combinations is different from permutations. There's an extra factorial on the bottom. It's 13 factorial over 13 minus 5 factorial times the 5 factorial, okay? And that gets us that, which gets us 1,287 ways. Goodness gracious, that's a lot of committees. Thanks, Mr. Box. Okay, you're okay with that? Good. Let's do B now. We've got to have 2 men and 3 women, so that's a bit of a restriction. I think the way to do that, guys, you try and think if you would work out how to do that. Well, I think what you've got to do is you've got to work out the number of ways of having the 2 men, and then secondly work out the number of ways of having 3 women, and then find a way to get them together into that committee of 5. So if we're choosing 2 men from 5 and 3 women from 8, let's do the men first. Number of combinations of men would be 5C2, choosing 2 from 5, and the number of combinations of women would be 8C3, choosing 3 from 8. But the thing is, guys, look, how do we get that information together into the single committee of 5 people? The fact of the matter is this. For every single one of those 5C2 committees of men, you have all of 8C3 different committees of women. So for every, I'll say it again, for every one of those 5C2 committees of men, you have all of 8C3 committees of women. So you must multiply those numbers together. Okay? You must multiply them. It's like a gigantic tree diagram again, yeah? That's the thing. So the total number of combinations would be 5C2 times 8C3, which apparently, according to Mr. Calculator, comes to 560 ways, and thank you, Mr. Box. You're happy with that? Oh, that's good. Now, we've got to do part C now. Let's go over the page for that. Now, this says we have to have at least 3 women, which in my way of thinking, that means 3 or 4 or 5 women. So we work out each of those scenarios individually and then add them up. That's all you do, guys. So for 3 women, we're choosing 3 women from 8, and that means as well 2 men from 5. That gets you the total committee size. So what's that? 8C3 times 5C2, which comes to 560 ways. For the second one, which is 4 women, which means we've got 1 man, we get, it's getting straightforward now, isn't it? You know what to do. 8C4 times 5C1, which is 350 ways. And for the 5 women, we don't have any men, okay? So that's just basically 8C5, choosing 5 from 8, and that's 56 ways. Now you add all those 3 numbers up, and you get the total number of committees. So it's 560 plus 350 plus 56, which is 966 committees. My goodness, committees everywhere. All right, so now this is the last question. And, oh, it's a probability question. Find the probability that a group of 8 cards held by a player of a card game will contain all those different bits and pieces. Let's do A first. No hearts. Well, the way you do probabilities, guys, is you work out the number of ways you can do what they're asking, and then you divide that by the number of ways of doing everything that's possible in terms of the hand of cards. Okay? I'll explain as I go. The first thing you've got to ask yourself is, of course, I forgot, does the order of the cards in the hand make a difference? Well, no, of course it doesn't. So therefore, we've got combinations. That's the first question you always need to ask. So, for this one, if we had no hearts, how many cards in the deck have we got available at our disposal to choose from? Well, there are 13 hearts. So if we don't have any hearts, we've got 52 minus 13 cards left, which is 39 cards. So really, we've only got a pool of 39 cards to choose 8 from, because we can't have any hearts, right? So the number of combinations of 8 cards from 39, it's excluding the 13 hearts, is 39C8, right? Now, we've got to divide that by the total number of ways that you can get 8 cards from a deck of 52. See, the number of combinations of 8 cards without restriction is 52C8, and we divide the first one by the second one, and that gets us our probability. Yeah, okay. What it is 39C8 over 52C8, which comes to, it was very complicated on the calculator, so I just did a decimal version of it. It was 0.0818. Thank you, Mr. Box. Okay, do you see that now? Probabilities? No problem at all. Let's do B. Oh, this one's a really nice one. At least 1 heart. Well, now you might think, good grief, how do I work that out? Look, it's easy. Because in the box above you can see the probability of getting no hearts. So therefore, getting 1 or more hearts is basically everything else. So basically, all we want to do is just work out 1 minus 0.0818, which apparently comes to something or other. What does it come to? Yes, I just had a little technical hitch there, guys, which I've unhitched. Okay, so let's go. It's basically just everything else. That's what it is. 1 minus the above, which comes to 0.9122, Mr. Box. Thanks. Now, wasn't that easy? You always look for those ones. When they say at least one of something, what you do is you work out the none scenario and then just take it away from 1. It's a nice little trick that you learn after a while from the School of Hard Knocks. So just tuck it away and use it. Good, we've done A and B. Now, C's over the page, I think. Yeah, hello, Mr. C. The 3 of diamonds. Heavens. Well, the probability that we've got the 3 of diamonds in our will contain the 3 of diamonds. Yeah, okay. Well, I think we've got to work out the number of ways we can contain the 3 of diamonds divided by the total number of ways of getting anything. So really, if the three of diamonds is absolutely certain, okay, in this scenario, we're saying, yes, we've got the three of diamonds. So if that's the case, then really we've only got 51 cards available for all the vagaries of combinations of things in our hand, yeah? So, and we've really only got 7 spots left in our hand because the three of diamonds is definitely there. So we're going to basically choose 7 cards from 51 for the three of diamonds scenario, okay? And therefore the probability of getting that will be 51C7 over the unrestricted situation for 8 cards, which is basically all the ways to get 8 cards out of the deck without restriction, which gets us 2 out of 13 apparently. Isn't that amazing? You like it? I think it's marvellous. Okay, now here comes D. This is the final kicker. This one looks really hard, but it actually isn't very hard when you see how to do it. The three of diamonds, given that there is a 3 in the hand. Well, look, the number of ways you can get the three of diamonds is 51C7 from above, yeah? Now, what that given thing does, look, it's basically a sheep in wolf's clothing. Okay, a sheep in wolf's clothing. It's not all that difficult. The given just means we narrow the field down to whatever they've told us. So really, what we've got to do, guys, is work out the number of ways of getting the three of diamonds, which we've done, and divide it by the total number of ways of having a 3 in the hand of anything, because we know there's a 3 in the hand. Okay, so that narrows the field down considerably. So what I want to do now is work out the number of ways of getting a 3 of anything and divide by that. Okay, that's the deal. Right, number of ways we can get any 3 is, okay, we could have 3 of diamonds, which we've got above. That's that, 51C7. Or we could have the 3 of hearts, which is the same number. Or we could have the 3 of clubs, which is the same number. Or we could have the 3 of spades, which is the same number. So that's the total number of ways we can have the 3 of anything. Those 4 things added up, right? So therefore, our probability of the 3 of diamonds is, yes, exactly. It's 51C7, which is the one for the 3 of diamonds, divided by the whole pool of getting a 3, which is the 4 of them, of 51C7. And of course, wouldn't you know it, it comes out to 1/4. Now, you knew that, didn't you? But it's very amazing to work it out that way. And I didn't actually twig myself until I worked it out. Then I thought, oh, you silly sausage, of course it's 1/4. But it helps to really consolidate your thinking, you know, when you sort of work them out that way. And really you get a robust understanding when you've done a few of these like that. I think that's all. I think I've just got a calculator dump on the next screen. Yeah, just to show you how to do the calculator thing. You just go to the menu and you'll see things like algebra, calculus, probability. And you select probability and there you'll see combinations. If you just put in, that was the one where I got 2/13ths for the 3 of diamonds. Okay, so it just allows you to put in the NCR thing. The N is the 51 and the R is the 7 over NCR for 52 and 8, and you get 2/13ths, yeah? It's easy, it's really easy as. So yeah, you go menu, and then you go probability, then you go combinations. And that's it. And we get the thumbs up, because it was mighty fine. Thank you all. Hope you enjoyed that. If you have any queries, just go back and have another look. And you could always consult your Year 11 textbook and just really go crazy on it if you like. But that's our top-up, okay? So thanks for being part of our top-up, and we'll see you next time. Okay, bye.